So, all right, so let's get started, everyone. So welcome back from break. So hopefully your break was so fun, relaxing, and also so tiring because you did a bunch of stuff. So today we're gonna so start the section on gradient descent. So how many people have seen gradient descent before in a previous course? So a few people, but not too many. Gradient descent is almost surely the most important algorithm in like all of machine learning. It's probably what most of the kind of CPU cycles are, probably used on nowadays. So it's probably one of the most important algorithms, ideas, approaches, in like all of computer science right now. So we're gonna, spend 3 lectures on it. So it's pretty important. The first lecture, this lecture is probably going to be more about the definitions. The punchline will come in the next lecture, and then we're going to kind of put everything together in the third lecture, where we're going to kind of talk about it, generically for the first 2 lectures, and then the third lecture is going to talk about it in the context of like actually doing data analysis. So it's a really important concept, and so we will do it. We had to wait. I think it was, there's kind of all this we kind of did some like foundational stuff and probability and linear algebra. Then we got to linear regression. Now we're doing some more sort of like foundational stuff again. The reason for delaying it is the third lecture will be showing how to do gradient descent to solve linear regression, and in fact polynomial regression. And it's going to be a really good illustration of how you use gradient descent to do data analysis. And it's basically going to be the same sort of structure we use there, which is really nice in the case of linear regression. There are lots of nice things that kind of tricks you can apply that makes things so simpler. Most of those tricks will apply more generally, but not always. So we'll kind of put everything together in this third lecture, and that will kind of give you a sense of where all the kind of like these CPU cycles are actually used in machine learning. When we talk about classification later on in the towards the end of the semester, we will again use gradient descent. So we'll talk about using gradient descent there. We won't actually kind of go through all of the mechanics again. We'll just kind of say, okay, here are the properties you need to run gradient descent. We'll set them up in this case, and then we'll at the very last lecture talk about some more advanced approaches that still use gradient descent, but don't always have all the nice, the properties you need. Okay, so this first lecture will be about what properties do you need to run gradient descent. The second lecture will be, okay, how do you run it? How do you know if it's actually working? And the third lecture will be on applying this onto data. All right, okay. In that context, homework 3 was out before break. I know a number of you have gotten started on it. If you had a break and you haven't gotten started on it, that's probably fine too, but you should get started on it soon. Homework 3 involves questions about linear regression, which we covered before break, and cross-validation, really important ideas. You're probably using Python in a bit more complicated ways than you did before. But if you remember, there's a link to a a tutorial on how to do a bunch of this stuff. A lot of the questions you probably have are answered in this tutorial on doing those things. So you'll have to stretch yourself a little bit. I know a lot of you are computer science majors or are somehow in computer science, so I think you should be okay. The last question on it will have to do with so the first part of gradient descent, and then homework 4, which we will post a little bit later, will be kind of putting everything together. We'll have to do is this third lecture where you're applying gradient descent towards linear regression, and that's going to be a little bit more complicated. Okay, but so kind of make sure you understand the parts in homework 3 to kind of build on that for the challenge in homework 4. So, okay. Yeah, I would say starting next week, it's probably the section of the class that, assuming you had the background probably in linear algebra, so that part wasn't very challenging. That is probably the most conceptually challenging for students to put everything together. The part on dimensional reduction involves like thinking about high dimensional data and linear algebra in ways that are kind of maybe beyond what you've seen before, and these are kind of conceptually more challenging for students. So try not to fall behind in that part of the course. We'll be around to help as you have questions. So okay, so any kind of questions of where we are in the schedule, what's going on, homework 3, early concerns? So great. So okay. All right. So gradient descent functions, and so gradients. The goal of this lecture is really to understand kind of the properties of functions that we need in general. All right. So the idea is that we're going to have domain X, and this in general is going to be RD. So think of this, the X coordinate as a d-dimensional domain, and we want to have a function. So in this domain, this will be the Y value will be f of X, right? So for every, remember a function, from every value of X, it gives you exactly one value on, the Y coordinate, okay? And we want to kind of ultimately, again, feeding forward in here, I'm going to change this notation just a little bit in a way that's intentional. I'm not going to use X, I'm going to use alpha instead as the parameter of the domain, because in general, we're going to use this where we're not going to think about the X coordinate as the data points anymore, but these are going to be the coefficients, the parameters that describe our model, right? Remember with gradient descent, we used alpha to describe these parameters. This are going to be the elements of the function, and f is going to be some sort of cost function, and we want to find the parameters which minimize this cost function. It's something we've seen several times in the course already. So we'd like to identify some point which is minimizing this, and to kind of really, we need to have some definitions to really kind of understand some subtle things about this. They can get extremely subtle, and I'm not going to go into all those details, but I'm going to give you kind of the high level so we can define things like a minimum and a maximum and a gradient, which is going to be needed to understand the properties of gradient descent. All right, so alpha is then going to be alpha 1, alpha 2, up to alpha d, right? So this is going to be the values we consider. And again, ultimately what we'll like to find is this alpha star, which is kind of the arg min, right? So this will be kind of the arg min over alpha of this function of alpha. So that's the point that corresponds with the minimum value of this of the function. Okay, so and how we're going to use this gradient descent is kind of largely about using calculus to find the derivatives, and this tells us how to kind of search over a function. When can we do this, and so it for this gradient descent algorithm to actually work. A lot of times this would probably be kind of a lecture for this would often kind of go through calculus in order to explain this. I'm going to try and we're eventually going to get to calculus, but I'm going to try and mostly defer the calculus as much as possible. I think it often hides the underlying structure of what's going on here. And so we want to think about this kind of structurally, and for me, this means geometrically. Okay, so what we need to do is define these minimum, maximum, and gradients. And the first definition we need neighborhood of a point, and in particular, we're going to use a ball as this neighborhood of a point P. Okay, this is going to be we'll say of a point alpha. So of a point alpha, the neighborhood is all the points in RD such that the distance between P and alpha, and we'll just use the 2 norm as the notion of distance, is less than or equal to R for some sort of radius, right? So if I draw a picture here, now this whole domain looks like RD. I'm going to have a point alpha, and so I could use any notion of distance or ball, but we can just use like a Euclidean ball, and you have some radius, and then all the points P within some distance here are going to be some neighborhood. Okay, and how large does the radius have to be? The radius just has to be so strictly greater than 0. So it has to be greater than 0, but it can be small, right? So I want to consider a small region around a point, alpha, and I just need to find some local region around it. So with the notion of a neighborhood, I can now define a minimum of some function f, right? So this is going to be is going to be a point alpha in RD. All P in the neighborhood of alpha have the function value of P is going to be greater or equal to the function value of alpha. Okay, so this holds for some BR, right? So as long as I can find some neighborhood, so this property is true, where R has to be greater than 0. It doesn't matter how small. This counts as a minimum of the function, right? So typically, if I don't restrict to this would sometimes be called a So a local minimum. And this might be, for instance, this would work for in this example here. If I looked at this alpha here, then I go up here and I can define some neighborhood around here, right? And in this neighborhood, if I look in this neighborhood, then the function value at alpha is lower than everything else in the neighborhood, right? So this would be so a local minimum. Okay, if I did not restrict to this ball, right? So I could say instead have a so global minimum of f is it's going to be a point alpha in RD, so that for all P in RD, I'm not restricting to a neighborhood, then f of P is greater or equal to f of so alpha. Okay, so if I don't restrict to some neighborhood, then this alpha I've drawn up here in green would not be a global minimum, because if I extend this neighborhood out here, I can find some other points near ace alpha star, which have a smaller function value. Yeah. Right before. Oh, yeah. So this is for all. Yeah, great. So for all. So for all P. Yeah, so if you haven't seen this symbol before, it means that for all P, it's like an upside down A. Yeah. So great. All right, I can also say a maximum of F is, this is going to be an alpha in RD, such that for all P in some neighborhood around alpha, that f of P is less or equal to f of alpha. Right. So this is kind of the opposite, right? And I can say if I restrict that this is an all D, then this means it's then that means it's going to be global instead of just a local minimum. Okay, I want to give another example here. Let's say I've got a function, right? This function f of x is equal to 3. It's a constant, right? So it doesn't matter what the value of x is here. Every value is going to be so exactly 3. So which points is there going to be a minimum here? Or is there going to be a maximum? What's going on here? Yep. So yes, right. So what is happening here is that you have, for any value alpha or alpha prime, right? So all of these values are the global min and also the global max, right? So those are the global min. Any value of alpha along here, right, is going to be the global min or the global max. This is somehow not very helpful in this, situation, right? Saying the global min or max is not giving me a lot of information. because all the function values are the same. Okay, so in this case, actually, is going to actually arise in some cases. If this is kind of a one-dimensional picture, but you could think of like a picture where it's, so kind of if you take, so like a half pipe, and you, so when you lay it flat, okay, there's a set of points along here, which are all going to be the global min, right? So you can imagine a function like this, and there are a bunch of, these global min points at all of the same function value. Okay, and so this is going to be a situation that we actually don't want, and this is going to come up sometimes, and we'd like to avoid this. And so there's a extra definition that if we can, so here, if we can get rid of this equal sign or equal to, then we will call this strict. So this would be a strict, I'll just say, so minimum would of f, this would be an alpha in RD, such that for all p in let's say so like a local neighborhood, or it could be global, it could be everywhere, then I would have the function value of p is going to be greater than the function value of alpha, and that needs to be strictly greater. It cannot be equal. Okay, so this case where the half pipe on the side, not like a snowboarding half pipe that's slanted down, but it's laying actually flat. There are a bunch of local min or global min that are all equally the smallest function value, the same in this constant function. Those aren't strict, so minimum. I need to be a strict minimum. I cannot have anything equal in the neighborhood. So in this picture, there were strict minimum at alpha and alpha star here, because everything in the neighborhood except for that point is so larger. So I would say except for set minus the point alpha. Okay, so everything in the neighborhood except for alpha, right? Maybe there's a easier way to see this for p not equal to alpha. Right, so if p equals to alpha, of course, they're going to have the same function value, they're the same point. But anything in the neighborhood not alpha is going to have a function value which is larger. That would make it a minimum. You can also have a strict maximum in the same way. Okay. All right, so there's another way of viewing this I like to think about a little bit. Again, this is, those pictures are in one dimension, but we'd like to think about this in higher dimensions. And what does this look like? We're going to have kind of a point alpha and some sort of local neighborhood around, so that's around alpha here. And I want to think that the function values are decreasing if I go in any direction from alpha. Remember, the radius can be arbitrarily small, so I just care about, is it decreasing or are these decreasing? And so let me color this. If it's decreasing in all directions, then alpha here is going to be a max. Okay, I could also think of another picture here where all the function values are moving into alpha, that the arrows are pointing in the direction that is decreasing, right? And so in this case, I'll color these regions as pink. So then in this case, alpha is going to be a min. Okay. So these are kind of the special points in there. Most points, if I look at most local neighbors on the function, right, of the function around alpha, there's going to be some sort of kind of property here where I'm moving, where the function values are decreasing, so across this line. The black curve is meant to represent all the points P that have the same value as so alpha. So if I put a P on here, then I would say f of P is equal to f of so alpha. And so then if I use my shading properties, these are moving kind of, these have function values above alpha, and these have function values smaller than alpha. And so in this case, we'd say alpha is going to be is going to be a regular point. Okay, most points are, almost all points you ever encounter are going to be regular points of the function. Okay, and that's where, you know, the function value is decreasing in a certain direction, and, you know, and ultimately we're going to want to find this direction where it's kind of it's increasing from alpha. Okay, almost all points are like alpha. The maximum and the minimum, aside from these special cases like this, are going to be kind of extremely rare. And in most cases, like numerically, we can almost never exactly find alpha min or alpha max. Okay, sometimes we can, like with the trick with like how this special formula where I can solve for linear regression, and I could automatically get alpha star, which is the minimum of the function. Well, there's kind of a trick there. We'll see how you actually, when you see how you actually calculate the inverse, that's kind of like an iterative process often. And so we're not actually totally exactly solving that point anyways, but that's kind of a special case that you can actually find the exact minimum. Almost every other case will basically almost always assume we're at one of these regular points where it's not a minimum or a maximum. Okay. The other reason I like to draw pictures like this is because there's this other type of point that is harder to understand without a picture like this. And that's where, let's see, I have alpha here, and let's say I've drawn one of these black lines, but maybe there's another line like this. And again, the black line are where all the points have the same function value as alpha. Okay, now I have some points which are going to be below alpha, and they're going to look like this. And the points which are above alpha look like this. Okay, and so what's happening is these pink regions, the function value is decreasing into alpha, and the green regions, it's decreasing so away from alpha. This is another sort of special point that's not a minimum or a maximum. This would be called, alpha is then going to be it's going to be called a saddle point, right? So if anyone here rides horses, you know, these sections are lower than the green sections are lower than the pink sections. So that's like, this is like a saddle. You're riding the saddle. You want your legs in the green region. Legs got to go someplace, and the pink regions are like there's, I don't know what's called, you know, a saddle that kind of goes up on either side so you don't slide off the horse, right? And so the saddle point is this kind of special point in the middle here, right? That is not a local minimum or a local maximum, but it's not a regular point either. Okay, and so as we'll see, you can define this with calculus as well, and that the gradient of this point is going to either be not defined or is going to be 0. And that's going to be like the minimum and maximum, but it's not the minimum or the maximum. These sort of, so saddle points come up in machine learning when we're running gradient descent in various cases, and they can be problematic. For instance, the gradient descent is going to want to find the gradient and follow the arrows down. And when if it gets to a point alpha, it could go one of two ways. So think of if you're standing on the top of like the Wasatch Range and it rains, a raindrop falls on the peak, and it could go down, or on kind of the point between the pass between two mountains, the raindrop could go down either way. It could go to Park City or kind of Heber in one direction, or down to Salt Lake City in the other direction. And so it ends up, the ultimate route of the water is different depending on some fairly arbitrary choice at this point. And so that makes understanding what's going on here more so, so kind of it's harder to deal with. It's kind of things, the analysis can be much more challenging. So we'd like to avoid these sort of points as well. But it's not a minimum or a maximum. Okay. All right, so how do you define a saddle point? The calculus way would say, kind of a technical definition would say, well, the gradient is 0, but it's not a minimum or a maximum. I would, in the book, I try and define it as if you look at the neighborhood around alpha, it has, if you don't count alpha, then it has disconnected regions of points above it and disconnected regions of points below it. The minimum and the maximum, they're all connected. The points above it are all kind of, there's only one region that's purple. You can have more complicated regions like this as well. You can have it, well, that's not here. I'll just make my alpha in the middle bigger, and that fixes that. And right, so you can have it so it has a bunch of these alternating sequences. So there are more complicated versions of saddle points that can come up as well. Okay, so it's not just two regions, but it could be like this as well. Yeah. So
the gradient defines the direction of steepest descent. So I was wondering, you said that like the saddle points present problems. So what does it always present a problem if the descent in the same directions are the same?
Yeah. So so people, this has been an area of study, kind of in intense studies. Some people machine learning the last 5 or 10 years, and there are a bunch of cases where it turns out there are saddle points, but it does not matter. And you would think, okay, it could be that there's some kind of picture where, okay, it can go either way, but then it eventually connects into the same region, right? So this might be the case here. It turns out this is not typically what's actually going on. It's usually that there's some sort of symmetry in the problem. Okay, so this is not really what's typically happening, but there's some symmetry in the problem, and you could, either way, we'll get to a solution which is going to be so equally as good, but think of like having like kind of 10 parameters, and the 7th or the 4th parameter, I could switch their roles, and I have to have them in one particular role. It has to have a certain value, but if I swap their values, it's going to give me the same answer. And so that's also will generate these sort of saddle point configurations, and that's more common. So, if this is the case, we have to think about it and deal with it. And it's in this course, aside from maybe the last lecture, we're not going to have to. We're gonna set up the problem so we don't need to worry about these. That's going to be our goal. So, all right. So the mathematics is there to tell you what you want to avoid. so you can design your algorithm so it doesn't have to deal with these cases, right? So think of like if there's an undefined behavior in some programming language, you don't want to use that undefined behavior, right? And so that's why we want to know about these saddle points, because we don't want to have to deal with them. So that's a perspective in this course, and in fancier advanced courses, may have to deal with these sort of things. Okay, so great. Okay, the main tool we're going to use to try and avoid a lot of these situations is dealing with what's called convex functions. Okay, so if we can, and we're mainly going to be doing this, so we're going to set up our functions so they are convex, then we're going to avoid having things like saddle points and like local minima, and then we can not have to worry about them. Okay, so there are other ways of dealing with this, but this is the main tool that people have used for many years to kind of avoid having to deal with these issues. All right, so I need to define what is a convex function. In order to do that, I'm going to start by thinking about how to define a line. Okay, so I'm going to look at a special way to define a line. Going through P and Q in RD. Okay, so I want to define a line. I'm going to call this LPQ. Okay, I like this definition because you can draw a picture and then you can write down the mathematics, and then that math will be useful for understanding the convex function sort of. So the definition for that. So these 2 points, P and Q, I'll draw them in 2 dimensions, but they could be higher dimensions. And I want a line that goes through here. Okay, think of a line that goes through P and Q. And I want to parameterize this line by some function. So L, P, and Q at, a value, lambda. Okay, and so I want, for every value lambda, I want to have a point on this line. And so for lambda equals to 0, I want it to be at exactly Q. For lambda equals to 1, I want it to be at exactly P. And for lambda somewhere in between 0 and 1, let's say 0.4, I want it to be somewhere in between P and Q. So if lambda is in between 0 and 1, it's going to be on this line segment in between P and Q. Okay, so there's a convenient way how to define this parameterization. Okay, so I write this as it's going to be the set of points defined as lambda P plus 1 minus lambda Q, such that lambda is is going to be a real value. Okay, right? So let's check that this works. If lambda is equal to 0, then the x I'm going to get, well, lambda times P is going to be 0 if lambda is 0, and 1 minus lambda, well, that's going to be 1 times Q. I'm going to get back Q, right? So if I set lambda equal to 0, I get back Q. If I set lambda equal to 1, I do 1 times P, that's P, plus 1 minus 1, that's 0, so the Q disappears. Okay, if I choose lambda equals to 0.5, what happens? I get half of P and half of Q, and so I'm taking the average of them, and I get exactly the midpoint. Yeah. If it's between 0 and 1, if I get them in here, this may be, I'll call this LPQ bar, might be a line segment. If it's between 0 and 1, that works. It gives me only the points between P and Q. It's kind of some weighted average of them, right? So if it's lambda equals 0.4, I'm basically getting 60% of Q and 40% of P. What happens if lambda is negative? But yeah, what happens if lambda is outside of 0, 1? Let's say lambda is so -1. What's going to happen? Yeah. Yeah. Okay, so let's say lambda, this would be lambda equals, so -1, right? Is going to be, and I go from 1 to 0 to -1, right? That's going to give me negative P, right, plus 1 minus -1, 2Q. Okay. Basically, I can view this as this point here as Q plus P. Let's see. Oh no, it's Q minus. Let's see. Have this backwards. Okay. It's going to be Q plus Q minus P. Is that right? Or it's so if I put in -1, I'm going to get, yeah. So I'm going to get. Let's write this out more carefully here, right? So the -1, I'd have minus P plus 1 minus -1 Q. 1 minus -1 is going to be 2. Yeah. So this is going to be 2Q minus P, which is going to be Q plus Q minus P. I didn't write that properly. Okay. I said the right thing. Okay. Q minus P. Okay. Q minus P, I can think of as a vector from P to Q, right? Q minus P is a vector from P to Q, and I'm gonna plus Q plus Q minus P, right? So I'm going to add that vector onto Q. So I'm going to start at Q, and I'm going to add a vector in this direction, exactly the length of the distance from P to Q. Okay? Okay, if I put in lambda equals to 2 or 3, or so let's say, so 1.5, right? Lambda equals to 1.5, right? What I'm going to be able to get here is I'm going to get P plus basically 1/2 of P minus Q. So, right, so I'm going to start at P and I'm going to go some direction away from P in that, on that same line. Okay, so this is a definition of a line. This is the same thing as like a linear combination of the points P and Q. Right, so if I just have the points P and Q, I can take the linear combination. If I restrict to 0, 1, this region in here is the convex, so combination of P and Q. This is for lambda in 0, 1. So when lambda is in 0, 1, I get the convex combination of P and Q. I get a linear combination of them. If I get, that gives me the whole line. But the convex combination is just the region there in the middle. Okay. Yeah.
So for higher dimensions,
no, it's the same formula for 2 points. You still get a line in higher dimensions. So a good way to think of one way to think of a line in higher dimensions. You could think of it either as the all the, the linear combination of the 2 points, so extending them this way, or I can think of a point P, and I can think of a vector from P to Q, and I can think of starting with point P and adding all scalings of that vector. It could be either positive or negative scalings, and I get everything on the line. Yeah. Okay. So this is a kind of a convenient way to think of a line. In higher dimensions, I can also think of like multiple points. I could think of a weighted combination of P, Q, and another point R. And then I can give positive weights to all the points, so those weights add up to 1. That also gives me a convex combination. That would be a convex hull. And I can generalize this to higher dimensions in other ways. But for now, we'll just think of these lines. Okay. Okay. So now I want to apply the same idea for a function instead. Okay. So now I'm going to have. Okay. So this will be RD. I'm going to have points P and Q, which are going to be in the domain RD. And now I'm going to have a function. Right, so this is F, and this is going to be F of alpha, the function values. Okay, and I want to check if this function is convex. I'm going to define it with a kind of an extension of this, so this formula. So I'm going to say F is convex if for all P and Q in our RD and all lambda in 0, 1. Okay, I'm going to have the following equation hold true. I'm going to have F of lambda P plus 1 minus lambda Q. So that's going to give me, right? So this will give me some point alpha that lies between P and Q, right? So this is in higher dimensions, but I can consider any P and Q in this higher dimensions and any point that's on the line between them, the convex combination of P and Q. So I want that this is less than or equal to lambda F of P plus 1 minus lambda F of Q. Okay, so now I've taken this lambda and 1 minus lambda, and I put these outside the function. Okay, so what is happening here? Now I want to think about these points. This is a point P, F of P, and this is in R D plus 1. I have another point here, Q, F of Q, right? Also in D plus 1 dimensions. I've got the D dimensions on my X drawn on the X axis here, and the one more dimension for the value of the function. Okay, and what this is giving me is implicitly there's a line between these D plus 1 dimensional points. Okay, and so now I can interpolate in between these function value at point P and the function value at point Q. And I need this to be larger, right? These function values here, I need these to be larger than the true function value, than the value at the blue function. Okay, so right, this is the blue function here, right? And so I need there to be a gap here. So I need that the green function, the shortcut, interpolating shortcut is always larger than the function. Okay, and so this covers for any 2 points, P and Q I pick in the domain. I've only drawn in 1 dimension, but I can pick any points in a D-dimensional space. I can look at the line between them. I can choose any alpha, any lambda, which gives me any alpha on the line between them. And I can evaluate this at the alpha. I can look at the function value at alpha, and I can look at the interpolating value. This is remember, this is f of lambda p plus 1 minus lambda q. And this point up here is lambda f of p plus 1 minus lambda f of q, right? So that point on the green line, that needs to be larger than the point on the true function value. And this holds for all points p and q, then the function is going to be convex. Okay. And okay, well, let me go back to this kind of simple but kind of silly example again. F of x equals to 3. Okay, is this function going to be convex? Yeah.
Are we usually given P and Q, or do we?
This holds for all P and Q. So this, again, this is the for all symbol, right? So this for all choices of P and Q, this has to hold. So if you can find any choice in P and Q where this does not hold, it's not going to be convex. Okay, so is this function going to be convex? Yes, this function is convex, right? So if I get rid of this or equal than sign, then it becomes strictly convex. This function is convex, but not strictly convex. Okay, and again, this is a simple illustration of it, but like that half pipe example, that function is not going to be strictly convex either, because I can pick those 2 points on the half pipe. Right, so I can pick, if I picked a point P and Q here, and I drew the line across here, okay, the function value is always going to be lower if I picked P prime and Q prime, but I can pick any P and Q. So if I pick P here and Q here, then these functions, the function value in between is going to be equal, which is not what you want. Okay, the strictly convex also, I need to make lambda between 0 and 1, but not equal to 0 or 1. Okay, so let me draw that. Okay, let's see. All right, let me just state a couple of, so convexity, so let me state a couple of functions, properties of convex functions. So for if f is convex, then a local min is also a global min. Okay, so if I find a local minimum, I know it's also going to be a global minimum if the function is going to be convex. Okay, so this is the main property that we're going to want here. We're not going to worry about local minima if we have convex functions. We also want, and if I know it's strictly convex, then the global minimum is going to be the only point which minimizes that function, right? So it's going to be the special optimal point, and there's no other points as good. Also, if I have F and G, which are convex, then I can define H as G plus F. This is also convex, or H is equal to the max of F and G. This is also convex. So if I add together functions, or I take a max, or I divide by a scalar, right? H equals F divided by beta, where this is a constant, then this is also convex. So I have these building blocks where if I start with simple convex functions and I add them together, or I take like a max, I can retain the convexity. So we're going to use these to be able to build convex functions that we want to take the minimum of. Yeah.
So for that second property, does that apply to just regular convexity, or does it have to be strictly convex?
Well, if you start with regular convexity, you're going to get back regular convexity. If you start with strict convexity, I think you get back strict convexity. Yeah, as well. Yeah. Yeah, so concave has different ways of defining it in the literature. It can sometimes just mean if you take a convex function and you take its negative, it becomes concave. But there are other ways concave is used to define other sorts of things. And so we're not really going to discuss that. We can discuss the negative of a convex function. That is probably what you're thinking about. And that can find the maximum. But we'll usually phrase things where we want to find the minimum, just out of, that's the convention. Yeah. Great. So how about I take a break for 3 minutes, and then we'll talk about gradients, and then this will go into gradient descent.
Just a quick question. I'm just wondering, back right here from the 2q minus p.
Yeah.
Equals q plus q plus p. I don't know how
Q minus P.
q minus p.
That did I? Sorry, I wasn't. Yeah. Ultimately, I think that's what I got to, but I know I mixed some stuff up in the intermediate.
Okay, so like, are you plugging something in for?
No, if you this is minus p plus 1 minus negative 1. This becomes a 2.
Yeah.
So I get 2q minus p.
Yeah.
Right? And so now I just expand it. 1q is by itself, and 1q is paired with the p. Right?
Oh, okay.
Yeah. And so then you can think of it as I'm starting at q and I'm moving in a vector. Right? This is a vector. This is the vector q minus p. So now I've started at q and I've moved by vector in the direction q minus p of the length, the distance between. Right? That's what q minus p, this vector means. And so that's how I can get to this point. That's you can also just kind of yeah, there are other ways of seeing it, but that's one way of thinking about it.
Okay. Yeah, I just want to double check.
Yeah. And you'll always, if I do this for like lambda 1.5, right, you'll always start with P or Q, and then you'll get some factor times this, right? This will give me P plus 0.5 times P minus Q. Right, I'll always be able to factor them in that way, and that's kind of why the equations work the way they do.
Okay, cool. Thank you for the clarification. Real quick, this is a simple question. What does this mean? Like, does that mean it's either F or G, which is bigger?
Correct. I plug in a value X for F and G, and I compute that value, the function value for F at X and at G at X, and I return the maximum of those.
So how does that give you a function and not just a value?
This works with think of it like a function in code, right? And I pass in functions F and G, and I pass in a parameter X. For every parameter X, or F and G are built into the function, right? For every parameter X, I compute F, I compute G, and I return the maximum of those two values. So it takes in X and it returns a value. So for every X, it gives me a value. This could be, let's do an example here. Let's say this is F, and this is G. Okay, and so now I'm going to get, this is going to be H, right? So if I take in a value or alpha, I'm going to evaluate at F, I'm going to evaluate G, I'm going to return the maximum of the two, and that's what H is doing.
Okay, that makes sense. Thank you.
Yeah. So great. So let's get back to it. All right. So just review. Convex functions give you this property. This is a very important property, that the local min, if you find a local min, that's also going to be the global min, right? So we can kind of take some function and kind of think about keep moving down until we kind of reach the bottom, and we don't have to worry about the situation like this one here, where we can get stuck in this green region, where we walk down to the bottom, we got to this alpha, and now there's no way to go down any further, you know? So like if you're at the Salt Lake, it's a basin, water goes down to the Salt Lake, it doesn't continue to go down to the ocean, it gets kind of stuck there, right? So that's not a convex function. I'd like to just follow the water on down until I get to the bottom, and I know that's the best I can do. With convex functions, you have this property that if you get to a local minimum, you know you're at the global minimum. Okay, so now we're going to go back and talk. In order to figure out how to get to the bottom, we've done this without calculus so far. We're going to need to find gradients, and these involve calculus. The calculus in this class is all going to be kind of easy sort of calculus, like polynomials, as it mostly turns out. A couple, maybe you'll end up taking kind of a gradient of like an exponential, but it will be easy, and that's by design, right? We're going to choose functions to take gradients of because we can choose those functions. We're going to choose ones that have easy to compute gradients, okay? Eventually we're going to go back to the sum of the squared errors, right? But the sum of the squared errors, one of the reasons is the gradients are going to be easy when we set stuff up. Okay, so if we have a function f of alpha, again, alpha is going to be in RD. So this is alpha. Think about this as a the domain of the function is multidimensional. Okay, and the tricky part about gradients is you have to deal with multidimensional derivatives. Okay, and they don't cover this initially in calculus class because it can get complicated. In this class, I think it won't get complicated. Everything we're gonna look at is gonna be pretty straightforward once you get kind of the main ideas here. So we're going to start with the function. Then the second thing we need to define the directional derivative is going to be a unit vector u. Remember, that means u is going to be say u1, up to ud. That's a d-dimensional vector, and we're going to say that the norm of this vector is 1. Okay, the norm of the vector is 1 is going to remove the scale information. So it's just pointing someplace, but it's not telling me, it's not really assigning a length to it. It's just a there's no real scale to it. It's just pointing in a direction. Okay, and then we're going to define the directional derivative, okay, as so follows. This is written, so this upside down triangle is called is going to be called a nabla symbol, N-A-B-L-A, okay, and so this is the derivative in the direction of u at the location alpha. Okay, at the position alpha is the point where you're taking the derivative, and it's in the direction u. Okay, this is defined. Well, I'm first going to define this with the kind of the standard definition of the derivative, and then we'll see other ways to think about it. We're going to take a limit of some value h as it goes to 0. We're going to say f of alpha plus h times u, right? Because my input is now d-dimensional, so I need to move in a direction u by a distance h. That distance h is going to 0, minus the original function value at alpha divided by h. Okay, so you've probably seen a form like this in a calculus class before without, you probably, maybe many of you have had some multi-dimensional derivatives before, but this is kind of the, one-dimensional, just a regular derivative, except you just thought of alpha as being a scalar value and h was a scalar. I didn't need the u, but now I need to pick a direction. Okay, and we're only going to consider this when this directional derivative is so well defined everywhere. Okay, if this directional derivative is well defined for all choices of alpha and u, then we say that this is so differentiable. Okay, and we're going to only consider differentiable. Well, that's not entirely true. For now, we're just going to consider differentiable functions. In the classification part of the class, you're sometimes going to want to handle non-differentiable functions, but you will deal with strategies to deal with these later. There's still going to be, we're going to at least need the functions to be so continuous. Oh, I forgot to define continuous functions before. Continuous functions are ones that don't have a jump. Okay, there's a lot of nuanced definitions to what it means to be continuous. We're not going to worry about those so much, right? Yeah, so let's see. This function is continuous. This function where there's a jump is not so continuous. The derivative is not defined at the discontinuity, for instance, right? So we don't want to deal with those sort of functions. There are other places where derivative might not be defined. Those will be more benign, and we can kind of ignore those, and those will come up. But these discontinuous functions, we generally don't want.
I know you said you're kind of avoiding the defining continuity, but what about like the sharp points and stuff? Is that also, those also well defined?
Well, those are continuous. You could think of the L1 cost function is going to be one common example, right? Where if I have, as I move further away from this point, I get a cost, and it's the derivative, it's continuous at this point, but the derivative is not well defined. But it's defined on either side, so maybe it's okay. So these are kind of situations that will arise. In the back? Yeah, so no, this is the nabla again. This is a nabla symbol. In LaTeX is /nabla. It's an upside down triangle. It means it's the symbol used for the directional derivative in the direction u of the function f at the value alpha. That's what this is saying. Oh, if this is for all alpha and u, alpha comma u. Sorry. Yeah. Yes. Yeah. There's lots of nuance that goes into this that I'm not going to go into. All right, but if that's enough for you, then great. Let's not dwell on it too much. You can take a class in the math department. They can go on some definitions for a few lectures if you want. And sometimes these do come up and they are important to understand, but we're going to kind of punt on those things. There's always more depth the mathematics can go into, and sometimes that's useful, and sometimes it's not. Okay, so I want to define this, but this is kind of, okay, this is not a fun definition to actually work with. We're going to compute stuff. So I want to look at some fairly specific unit choices of unit vectors, right? So I'm going to consider unit vectors called E1, E2 up to ED, okay? So general EI is going to be a specific unit vector that's going to have this simple form where this is the ith coordinate. It's all zeros vector, except the ith coordinate is 1. Okay, the norm of this is 1. It's a unit vector. There are d unit vectors like this, right? So I can take the directional derivative with respect to these unit vectors. These will be useful and they're easy to compute. Okay. Okay. So I'm going to say that nabla I of f of alpha will just be shorthand for nabla ei f of alpha. Okay. So I'll just use the ith, and what this helps me do is this isolates the ith coordinate. Okay, so I'm going to have d coordinates. I want to isolate the ith one, and this is equal to the partial derivative of the ith coordinate of alpha. Okay, so I can take the partial derivative now. With the partial derivative, if you remember, is I'm saying, well, the alpha I variable, that is still a variable. All the other variables are going to assume constant. Okay, so when I assume a variable is constant, then the derivatives are easy. I can basically, mostly ignore them. All right, when I choose this particular unit vector, then I can take the partial derivative with respect to the ith coordinate of my parameter. Yeah. Yeah, the ith, so coordinates, chord, C-O-O-R-D, what I meant right there. Okay, so that's the ith coordinate is 1, the rest are 0. Okay, okay, and this will be equal to the partial derivative just at I. Okay, okay, and so now, this allows me to define the gradient of F. Okay, this is going to be written as just nabla of F with no kind of a U in front there. Okay, and this is going to be equal to the partial derivative of F at d alpha 1 times the vector E1 plus partial derivative of F alpha 2 E2. So if I can take all these partial derivatives, if you remember, each of them is the partial derivative is just like a one-dimensional derivative, a regular derivative. So it gives me kind of so it's just a function of one yeah. So it's just a function, but I'm going to multiply them by these vectors, E1 through ED, each of them. Okay, and this is equivalent to just putting them into a vector, df, d alpha, df, d alpha 2, df, d alpha d. Okay, so this means that the gradient is going to be a function from RD to RD. Each of the partial derivatives is a function value that gives me the output. The range is a scalar, but the gradient, the output is going to be a vector value here. Yeah.
So is that top line should be the gradient dot F?
The gradient, that's how I write of, sorry.
Oh, no, I mean, so in the top line, it's returning scalar value, but in the second line, it's a vector.
No, the top line is a vector value too. Each of the E1s is a vector. So I'm taking a scalar, right? So yeah, this is a good question. This component is a scalar. This is a vector. A scalar times a vector is a vector. Now I'm adding together vectors. Now this kind of it's a pretty silly vector, right? Remember what E1 is. It's a 1 then a bunch of zeros. So I'm taking that scalar value in pink, I'm multiplying it by 1, and that's going into the first coordinate, and its contribution to the other coordinates is all zeros, right? The second term there, I get a scalar value multiplied by E2. That's a 0 times a 1 times a bunch of zeros. So that's why the second term in the vector is only that partial derivative, right? Okay, so this is the gradient. Okay, so I want to go through an example, and I have 2 minutes left. Okay, so I'm going to say something really quick, and then we'll review this in the next lecture, and then we'll go through a very quick example of this. But the gradient is going to be the direction plus a scale in the steepest increase. Okay, so I'm gonna, if I have a function, it's a bit hard to draw now because I need to think of a function at least in 2 dimensions. It's gonna point in the direction where the function value is increasing the most. And so I want to actually, to go decrease, I want to take the negative of the gradient. Okay, and we'll see that next time. But this gradient will tell me the direction of things increasing the most. Okay, just to make clear, let me look at an example here. Okay, so let's say alpha goes x, y, z. So we're in R3. And so I have a function value of x, y, z is going to be equal to 3x squared minus 2y cubed minus 2x e to the z. This will be about as more complicated than we'll mostly be dealing with here, okay? And so I want to take the gradient of this, Okay, and the gradient, okay, I need to take the partial derivative first with respect to x. The partial derivative with respect to x, well, I'm going to get 6x. That's from the first term. And I also need this last term has a component 2e to the z, right? So that's the gradient with respect to partial derivative with respect to x. Partial derivative with respect to y is only from the second term. Again, I'm going to get negative 6y squared. And then the third term, if you remember, x is now a constant in front. The partial derivative with respect to z, if you remember e to the z, its gradient is itself. So I'm going to get back negative 2e to the z is the third term. Okay, now I can evaluate the gradient of f at some values, 3, minus 2, 1. And I just evaluate this by plugging these in. And I'm going to get, let's see, for the x, I get 18 minus, so 18 minus 2e times the value of z, which is 1. So that's the first coordinate. The second coordinate is y, I put in minus 2, that's 4 squared, that's minus 24. And the last coordinate, x is 3, that's a 6, negative 6 in front, times e. Okay, great. So the output is a three-dimensional vector, not necessarily a unit vector. It has some scale to it. Okay, question. Because it's a coefficient. I do. It's a constant, just like 2 is a constant, right? Yeah. So it's that's probably a little bit rusty in these things. That's fine. This will be more complicated than what we'll actually need to do. I'll basically tell you what the partial derivative is. I'll pre-compute it for all linear regression for you. It'll be easy. Okay, great. So we'll stop here and I'll review what gradients are next lecture, and then we'll see how to use them.